proofs using circle theorems. So here we're going to look at all the circle theorems we've looked at so far and doing some proofs to solve for certain variables. Okay, let's draw up a diagram. So here we've got our circle with the center, and we're going to draw some radii coming off the center. Draw in some chords. So let's call this point A, B, C, and D. We'll call the center O. We're going to draw perpendicular. We're going to line going to the center, and same over here. Let's call this point E, and this one point F. We know that OE is going to be 3 centimeters. We know this angle here is going to be 100 degrees. And we know the length of this chord is going to be 8 centimeters. And the first thing we want to do is find the length of OF. So OF is this one here, and we can use the fact that chords of equal length are equidistant from the center. Okay, so sorry, we also know that 8B is also equal to 8 centimeters. We have to know that the chords are of equal length. So chords of equal length are equidistant from the center. So if this one's 3 centimeters, if this chord is 3 centimeters away from the center, this one has to be as well. So we can say that OF equals OE, which would equal 3 centimeters, and we have to write the reason that chords of equal length are equidistant from the center. All right, next we want to find DF. So let's have a look where DF is. DF is down here. And we can say that DF has to actually be half of the length of this chord, because we can use the fact that perpendicular from the center, from the chord to the center, actually bisects the chord. So this means it cuts it in half, and it means that these have to be equal in length. So we can say DF actually equals half of DC, or DC divided by 2. DC is 8, so 8 divided by 2, which is going to be 4 centimeters. And the reason is that the perpendicular from the chord to the center bisects the chord. Okay. Lastly, for this one, we want to find the angle AOB. Let's have a look where that is. So AOB is this one here. And we can actually say that angle AOB is going to equal angle DOC. This one here. And it's going to equal 100 degrees. And the reason for that is chords of equal length So these two chords of equal length subtend equal angles at the center. So these two chords of equal length make equal angles at the center. So let's write that out. Chords of equal length subtend equal angles at the center. Okay, let's look at another example. So let's draw our center in. It's going to be 0.0. So let's draw some radii in. Then we're going to, on that same arc, we're going to draw some lines. And on the same arc, we're going to draw some more chords. And we know this angle in here is going to be 30 degrees. This one's going to be theta, and this one's going to be alpha. And let's call this point D, A, B, and C. Okay, so the first thing we want to do is figure out what theta is. So here, we're going to use the fact that the angle at the center is twice the angle at the circumference if they're standing on the same arc. And hopefully you can see that using this arc here, this angle at the center is on the same arc with this one at the circumference, and the angle at the center is twice the angle of two chords on the circumference if they're subtended on the same arc. So we can say that theta has to equal twice the angle ADB. So we can say it equals 2 times 30, which is 60 degrees. And the reason for that is that the angle at the center is twice the angle at the circumference okay. And now we want to find out what alpha is equal to. And if you have a look here, at this arc here, we can see that this angle standing on this arc is going to be the same as this angle standing on that same arc. So we can say that alpha is actually going to equal angle ADB. So it's going to equal 30 degrees because angles standing on the same arc are equal. Let's draw up another circle. This time we're going to draw some tangents going to an external point. And we're going to draw our center in and join the point of contact to the center. So we'll make that 190 degrees. This is going to be theta. Call this point P. A, O, and B. And we want to find theta. Okay. So to do this, I'm going to have to use a couple of properties. So first, if this angle's 190 degrees, we should be able to get the remaining angle on this side. So first we can say that angle AOB is going to equal 360 minus 190, going to give us 170 degrees. And the reason for that is just angle sum at a point equals 360 degrees. Now, we can also say that angle PAO is going to equal angle PBO, which equals 90 degrees. So let's just have a look at that. So angle PAO, so this one here, is going to equal angle PBO, 90 degrees. And the reason for that is we've got two tangents meeting up with a radius, and a tangent meeting with a radius always makes a 90-degree angle. So now we know that this angle here is 170. These ones are 90. Let's just write our reason. That angle between the tangent and radius equals 90 degrees. And now all we have is a quadrilateral here, and the angle sum of a quadrilateral is going to be 360, so we should be able to work out our required angle theta. So theta is just going to equal 360 minus 170 minus 90 minus 90, because an angle sum of a quadrilateral is 360 degrees, and that's going to give us, whoops, 19, should be 90, and that's going to give us 10 degrees for theta. All right, let's look at one more example. So let's draw in a secant and a tangent. Oops. Draw in our tangent, meeting an external point, and let's draw in another secant connecting this. Okay, there's going to be point P, this will be A, D, B, C, call this point Q. Now, we know BQ is going to be 1 meter, DQ is going to be 3 meters, CQ 2 meters, AQ is going to be X, which means that AC is just going to be x plus 2. We know AP is going to be 4 meters. DP we'll call Y. And first we're going to solve for x. We want to know what x is. Now, to solve for x, we can use our theorem of intersecting chords. Here we have two chords that intersect. So we can use the fact that AQ multiplied by CQ is going to equal BQ multiplied by DQ. So we've got AQ multiplied by CQ is going to equal BQ multiplied by DQ. So let's fill in everything we know. So AQ is x multiplied by CQ, which is 2, is going to equal BQ, which is 1, multiplied by DQ, which is 3. So we're just going to get 2x equals 3. So divide both sides by 2, and we're going to get x equals 1.5 meters. And now we know the length of x. And our reason for doing this was that we had our property of intercepts of intersecting chords. Now let's solve for y. Okay, so to solve for y, we now know that AC, this distance here, is going to be x plus 2. We know x is 1.5, so that's going to make that 3.5 meters now. We know the length of AC. And the reason that's going to help is because we can use our tangent and secant property, where PD squared is going to equal AP multiplied by CP. So where we get our tangent to the external point squared is going to be the bit extending out, AP, multiplied by the whole length of the secant, CP. Let's put in everything we know. So PD is just y, so it's going to be y squared equals AP, which is 4, multiplied by CP, which is going to be the whole length CP. So we've got the 3.5 plus 4 to give us 7.5. So we're going to get y squared, 4 times 7.5 is 30. So now we can square root both sides, and square root of 30 is going to be 5.48 to 2 decimal places. And the reason for that was our intersecting of the tangent and secant theorem.